Welcome to the Hardware and Networking Advanced Concepts and Troubleshooting course. The CompTIA A+ certification is a common gateway to a new career as a technology expert. This certification will prepare you for training and skills required for Core 1. When you are A+ certified, people understand that you have a strong understanding of IT concepts and that you have the skills to set up, configure, and troubleshoot common devices, networks, and systems. To successfully complete this course, you should have basic knowledge of IT fundamentals, basic IT setup and troubleshooting skills. The prerequisites for this course are Introduction to Hardware and Operating Systems, Introduction to Networking and Storage. This course is the next step from the Professional Certificate Series of IBM courses intended to help you develop IT fundamental skills and knowledge. When you complete this course, you'll be able to investigate more detailed information about various hardware so you can more effectively differentiate, configure, and troubleshoot a variety of hardware types when issues arise. Uncover more detail about network and storage types, including hardware and specialized tools specific to networking and storage, and see how to set up and troubleshoot multiple configurations. Determine the physical and technological specifications of internal computer components, and then learn about common issues for each component type, so that you can easily recognize, configure, and troubleshoot common component-related problems. Discover common printer types so you can identify their physical differences, see how each type works, and apply basic maintenance and troubleshooting for each type. The Professional Certificate Series of courses helps you prepare for CompTIA IT Fundamentals, ITF Plus certification. This course provides additional information and application opportunities that build upon the preceding course series to help you prepare for the CompTIA A+ certification. Move up to the next level. Guided instructional videos walk you through key concepts with essential need-to-know facts. Interactive activities reinforce what you've learned in videos, and virtual hands-on labs get you to apply new knowledge and skills as you learn. Forums provide connections where you can introduce yourself to others, provide feedback, and get support. Practice assessments help you gauge your knowledge, and graded assessments prove what you've learned, leading to a shareable badge and certificate that you can show prospective employers. And a mock exam helps you bring all your knowledge together and familiarizes you with the certification testing process. We're here to support your success, and we're excited that you're here. Let's get started. Welcome to the Laptop Components course. After watching this video, you will be able to describe the difference between laptops and desktops, identify laptop components by their function, and explain how to install, configure, and maintain laptop components. Desktops are generally larger, more powerful PCs with better heat dissipation. Laptop PCs are more portable. Being able to use a laptop from anywhere is very convenient, which makes them a popular choice. Both laptops and desktop computers can have large amounts of memory and storage, but desktop computers often have more room for expansion and can have more powerful graphics cards. Additionally, desktop computers are easier to upgrade because they are larger with more accessible components. Mini PCs are small form factor desktop PCs that have fewer ports and less power. They can't be upgraded like standard desktops and also don't have as many high-end features because they don't have the space. Mini PCs often have efficient processors, compact storage, integrated graphics as opposed to dedicated graphics cards, and attractive pricing, usually much lower cost than regular desktops. They are a smaller and less powerful alternative to desktops. Here are the common components of a laptop. The processor, also called the Central Processing Unit, or CPU, executes the instructions that run the operating system, applications, and more. RAM, random access memory, is a type of memory that a CPU uses to process instructions. The hard drive is a storage device that stores the operating system, applications, and data files. The display is the screen of the laptop. The keyboard inputs the data and commands that a user types. The touchpad controls the cursor on the display. Laptop batteries provide power so the laptop can be used on the go. The motherboard is the main circuit board of the laptop and contains the CPU, memory, and other components. The cooling system dissipates heat from the processor and other components. Laptops typically have a variety of ports, such as USB, HDMI, and audio, that can be used to connect to external devices or peripherals. Random access memory, or RAM, is a temporary data storage that a CPU uses to run faster. There are two main types of RAM: static RAM, or SRAM, and dynamic RAM, or DRAM. SRAM is faster and holds data as long as there is power, but it is more expensive. DRAM is slower and requires constant power refreshes to retain data, but it is less expensive. Synchronous DRAM, or SDRAM, synchronizes memory speeds with the CPU clock to increase the number of instructions per cycle. Double data rate, or DDR, is a set of standards for SDRAM that tells it how to work. DDR was released in 1998. The latest version, DDR5, was released in 2020. A dual inline memory module, or DIMM, is a hardware component that plugs into a socket on a motherboard. DIMMs provide SDRAM. DIMMs are easy to replace or upgrade via the motherboard sockets. There are also SODIMMs and micro-DIMMs, which are smaller DIMMs used in laptops and other small devices. Lithium-ion or Li-ion batteries used in laptops. There are also SODIMMs and micro-DIMMs, which are smaller DIMMs used in laptops and other small devices. Lithium-ion or Li-ion batteries and lithium-ion polymer or LiPo batteries are great for laptops because they are rechargeable and have high energy density. They do not suffer from the memory effect, where capacity is reduced if they are not fully discharged before being recharged. To maximize laptop battery lifespan, charge laptop batteries when they are low and avoid extreme temperatures. There are a few factors that can make a laptop easier or harder to repair. Design. Some laptops are designed with repairability in mind, which means that components like the RAM, hard drive, and battery are easily accessible and can be replaced or upgraded without much difficulty. Other laptops may be more tightly sealed, making it harder to access and replace components. Components. Laptops that use standard, widely available components are generally easier to repair because replacement parts are readily available. Laptops that use proprietary components may be more difficult to repair because specialized parts may be hard to come by. Documentation. Some laptop manufacturers provide detailed documentation and instructions for repairing their products, which can make the process easier for technicians. Others may not provide as much information, which can make it more difficult to diagnose and fix problems. Warranty. Some laptops come with long warranties that cover repairs, which can make it easier for users to get their laptops fixed if something goes wrong. Others may not have as comprehensive warranties, which can make it harder or more expensive to get repairs done. In general, laptops that are designed with repairability in mind and use standard, widely available components are generally easier to repair. Here are some general tips for installing and configuring laptop components. Laptop batteries may require you to adjust the operating system's power management settings to optimize battery life. Laptop keyboards and keys are cleaned by gently wiping with a soft cloth and mild cleaning solution. You can also use compressed air to remove debris trapped beneath the keys. Laptop memory is commonly replaced via a small door on the side, back, or bottom of a laptop. Note that some laptop modules require you to dismantle the laptop and remove the keyboard and other components before being able to access the motherboard sockets that house the replaceable memory modules. Biometric sensors are cleaned with a soft cloth and mild cleaning solution. Near-field communication, NFC, must be enabled in the operating system before you repair it with an NFC-enabled device. When you install, configure, troubleshoot, and replace laptop components, always follow manufacturer's instructions. And always use the appropriate tools and protective measures to keep your components and system free from damage. If components stop functioning properly, run updates, run antivirus software, troubleshoot, or replace. In this video, you learned that both laptops and desktops have large amounts of memory and storage, but laptops are portable, while desktops are powerful. The processor or CPU executes instructions that run the operating system. RAM is memory the CPU uses to process instructions. The hard drive stores the OS, apps, and files. The motherboard is the main circuit board of the laptop. The cooling system dissipates heat from the processor. Additional laptop components include the display, keyboard, touchpad, battery, ports, and sometimes biometrics and NFC.
Welcome to the software development process and
work. But if they got halfway through building it and they saw a huge crack in the concrete, they'd be able to identify and fix that. And if it was completely done and water was flowing straight through,
As we know, software is quickly becoming an integral part of human life as we see more and more automation and technical advancement. Just like we expect car to work all the time and can't afford to break or reboot unexpectedly, software industry needs to continue to learn better ways to build software if it were to become an integral part of human life. And that's the motivation for this course.
in this course, we're going to start with a closer look at several aspects of the SDLC process, which will be included in any of the models, from waterfall to agile and beyond. Things like, how do you understand what the users really want? How to effectively communicate the design to your colleagues? What are the best practices for deploying your solution when you're done? And what approaches you should use to test your project throughout the entire process.
And then once we learn about the core software development processes, we will learn about some of the industry and the standard methodologies. What are the pros and cons of each? You will learn enough to have meaningful conversation around the software development processes in your teams. In week 3, you will learn about traditional software development models like waterfall, V model, sashimi, and rational unified process. In week 4, we'll learn about agile mindset and get an overview of some of the common agile and lean software development models. Apart from quizzes, you will also be doing 2 peer reviews projects where you will be using a fictional case study and you will have to identify software development models you would recommend to use and why.
At the end of the course, you should be able to apply core software engineering practices at a conceptual level for any given problem.
And then also you'll be able to compare and contrast traditional, agile, and lean software development methodologies at a very high level. These includes waterfall, rational, V model, incremental, spiral models, an overview of agile mindset, and few agile models. You will also learn how to propose a methodology best suited for a given situations. If you're doing this course as part of the specialization, then there are 3 additional courses that will give you deeper understanding of this subject. So the first course is going to be the Agile Software Development, and we will start again by a deeper understanding of Agile principles and methodologies. Then we'll talk about how do you apply Agile mindset on a software development project. We'll learn about Scrum and XP. And then in the third course, we'll learn about lean software development, where we will again start from what are the origins of lean, what are from the manufacturing that we got. We'll learn about some of the principles, and then we'll learn about some of the ways to apply lean methods into software development using value stream mapping, using Kanban, design thinking, and lean startup. I'll be teaching these 2 courses. And finally, Kevin will be teaching engineering practices for building quality software.
In that course, we're going to be covering a variety of things that drive into quality. Making it work right is one thing, but doing it well is another. So we'll be talking a lot about things like coupling and cohesion. That is, how well your code works together is related to a single focus, and how well different modules work together, or don't, in order to make it modular, in order to be able to swap things out. We'll also be talking about things like the solid principles and a variety of other quality metrics of how you can look at, measure, and then act upon the quality of your software.
In this lesson, you're going to learn about what software development looks like. So what you will hear or see if you're part of a software development team. I'm also going to take you through a journey that software industry took over last several years. That means you're going to hear a lot of new terms. So fasten your seatbelt as you're about to get overwhelmed. The idea is to give you the summary of what this course is going to be about. Before we get into a software development process, let's take a look at a process that you might be familiar with, like building a house. So if you were to build a house, you will probably reach out to a builder and tell about your needs. Like, I need 2 bedrooms, I need a bigger great room, I need a room on the basement, and yada, yada, yada. And builders may give you some option, and then you will have to do some analysis and come back with your choice. In the end of this phase, you will come up with exactly what you're looking for. Then builder is going to go back and going to create a floor plan, and then he's going to show it to you the floor plan, and you might make some adjustment. Once that is done, builder is going to create a detailed map or detailed plan about where the foundation is going to be, where the electricity is going to be, where the plugs are going to be, where the plumbing is going to be, and then they're going to start building the home. And as they are building the home, they're going to call the inspection people to come and inspect the house. For example, let's say the foundation is done, they're going to get the foundation approved. When the plumbing is done, they're going to get the plumbing approved, and so on. And once the house is ready, he's going to call you to say whether you like the house, is it what you expected? And then once you approve it, then you're going to start staying in that house or living in that house. And of course, there comes the maintenance of the house. Let's see how software development is similar or different than this. So when you are building a software, similar to the building a house, you're looking at requirements, or you're looking at what exactly you need to build. And during that time, you will do analysis of different options, or you might do a prototype and show it to your customer and just say, is this what you're looking for? But at the end of this phase, you have exactly what you're looking to build. Then comes the architects and the software developers. They're going to design the system, they're going to architect the system and say what are the different components that they need to build and how they're going to work together. Once the design is done, they're going to start coding and start doing unit testing. So each of the sub-teams are going to start building their components and test it. Once all the components are ready, they're going to bring all of these components together and do integration testing, or called verification, and they will do functional testing. And when the software is ready from the developer point of view, then they're going to invite the user, and they will do a testing called UAT, user acceptance testing, in which a user says, yep, this is what I was looking for. Oh no, this is not what I was looking for. And then once everything is done, then the software goes into production, which means the user is going to start using, and they might ask for some changes, or you may have to fix some defects and so on. So that's called the operation and maintenance. So as you can see, it's quite similar to building a house. The model that we just reviewed is called a waterfall method, where you go from phase to phase to phase: requirements, design, implementation. As industry started to use this method, they ran into several issues. For example, they found that it's very difficult to predict the requirements 1 year or 2 years ahead. As the market changes, or sometimes it's just very difficult to predict what a user will like or not like. And since the cycle is a year or 2 year, it is possible that the developers or the architects misinterpreted the requirements. And so that misinterpretation will go undetected all the way to design, implementation, and the verification. And similarly, the integration issues between the different components go undetected for a year while the software is being developed. So as these issues were coming up, other variants of waterfall started to evolve, like a V model, which focuses a lot on testing, or sashimi model or RUP model that focuses a lot on overlapping different phases. And then the incremental model, where you do the requirements in one shot, but then you do the design, testing, and deployment in increments. And then there's a spiral model, which is a very risk-driven approach. As all of these variants were coming along, there was another thought process that were evolving in the software industry called agile. So agile is not a model, it's a mindset. There were a lot of thought leaders in software industry that were building the software very successfully. And so they came together and said, what is it that we are doing that is making us successful? And they articulated what we call now the Agile Manifesto and Principles. And as this manifesto and principles were crafted, there were models like Scrum and Kanban and XP that helped implement this mindset, that promote this mindset. And so you can see it's not just these three, but many other models came into being. The basic idea behind all of this model was that instead of building this whole 1-year cycle, you build in short cycles. So you define little, you build, you test, and you learn. And then again, you just keep doing this. That way you can adjust to the market quickly, and then you are learning from your users quickly. And so the change became a norm because after every cycle, you may have a change. And so software industry also has to learn how to respond to this change quickly and confidently. And the idea of continuous integration, where a developer who is building the code, as soon as he commits the code or as soon as he finishes the code, it's integrated with all the other components of that software. And then all the tests that verifies whether the system is running are run. They are called the automated testing. So as soon as you commit a code, all of the test is tested to make sure nothing else is broken in the system. And all of these deployment is automated. So as soon as the code is committed, it's deployed automatically so that there is no manual errors, and as well as it reduces the effort to deploy a code. And not only just these three, many other practices evolved. And so the safety net of automated testing and this automation help developers respond quickly and confidently to the changes. This also led to a new partnership between the developers and the operations. They marched towards a common goal, and that led to a culture of DevOps. Now, as this model of Agile was getting popular in industry in a smaller scale, people started to wonder, can we apply this on a bigger projects? And hence, many new models evolved, like scaled agile framework, large scale Scrum, and disciplined agile framework. Sounds complicated, and they are, and many organizations are trying to use this model and are successful, but the jury is still out there around the effectiveness of these models. So from 1-year to 2-year life cycle, the industry moved to a smaller cycles, but then they wanted to learn if there is a cheaper and a faster way to learn. And the concepts like lean startup and design thinking came into being, where you find the cheapest way to learn the one cycle. An example is Zappos.com. They wanted to sell shoes online. And since this was a new concept, they didn't know if somebody is going to buy shoes online. And so instead of building a whole new infrastructure of inventory of shoes, they just created a website and said, let's see if people buy. If people will buy, I'll go to a store, buy the shoe, and then ship it to the customer. And they did it, and they were successful, and then they started adding infrastructure. So the same concept that was applicable in startup started to evolve and being adopted in the enterprise as well. And this also led to team members or the organization to focus on the outcome and not just the output that they are building. And as all of these process and methodologies were evolving, industry also realized that process is just a part of the puzzle. We have to think about some soft issues like psychological safety or motivation about motivations of the individuals and growth mindset and many other concepts like this. So as you can see, software industry has evolved quite a bit in last several years, and it's continuing to get better and better.
Hi. In this video, we'll be talking a